Okay, this is a second video for lesson 1.4, transformations of functions. This is an example of how to do a mapping notation equation. So what I've done for this is I picked one of the more difficult parent functions to transform, and that's the rational function f of x equals 1 over x. And our goal is to sketch a graph using mapping notation. When we start this process, you always want to start by graphing the parent function. So I've done that for you by graphing the two arms of the rational function f of x equals 1 over x. And the part that actually doesn't show up on this graph but does exist in the rational function is two asymptotes. There's a vertical asymptote that goes through the y-axis, which has the equation x equals 0. And there's a horizontal asymptote that goes across the x-axis with the equation y equals 0. And these asymptotes are important because over those through those values of x equals 0 and y equals 0, the function does not exist, and we have no definition for the function there, or you can say it's undefined. Why this is significant is that while we transform the graph, we have to shift those asymptotes. So any shift to the left or right would be shifting our vertical asymptote left or right. As we shift our graph up and down, we'd be shifting the horizontal asymptote up and down. And actually, that's the best way to create your transform graph is by using the horizontal shifts to shift the vertical asymptote and the vertical shifts to shift the horizontal asymptote. So, like I said, we're going to start with the graph. If you can't produce a graph of your parent function, or you don't remember the graph of your parent function and the key values, you can construct a table of values and plug in numbers to the equation to get your y values. For example, if we didn't remember what this graph looked like, we could use x values of -2, -1, 0, 1, and 2, plug them in for x, and get your y values that way, and you'd have a graph that's similar to the one that we're going to produce. And that will always work for any parent function. But sometimes it's easier just to remember the key values or remember the shape, and then the key values might come with it. So we're going to assume that you have the graph and our key values before we do our mapping notation. In order to use mapping notation to transform, we need to take our transformation equation, which in this case is y equals 2 f x plus 4 minus 3, and try to pick out the transformations so we can write our mapping notation. Your transformations will always follow the structure of a times our function, and then in brackets, k times x minus d plus c. And if we try to match up piece by piece, we can pick out a, k, c, and d. So right in front of f is where a should be, so there's our a. Right in front of x is where k should be, and if we look in front of x, we actually have the number 1, so we have a k of 1. D should be following x. If we box that, we have a d, but remember the opposite sign, because in our transformation equation with just letters we have negative d, and in our function we have positive 4, so we're going to have to flip the sign to get what positive d is. And c should be at the end of our equation, -3 and c. So altogether, that would give you an a of 2, a k of 1, a d of -4, and a c of -3. Once we have our a, k, c, and d, we can plug it into our mapping notation. Our mapping notation is x over k plus d, ay plus c. But on our handout we just have x plus d, and that's because I already knew k was 1 when I made the handout and I left it off. So we just have to take our x and add d. D is -4, so we have x minus 4 as our mapping for our x, and for our y we would have 2y minus 3. And now we can just take our x values and apply the transformation to get our new x value. So we have -1 minus 4 is -5. -1/2 minus 4 would be -4/2 or -9/2. Oh, sorry, -4.5 or -9/2. We have 0 minus 4 would be -4. A half minus 4 would be negative 3.5 or negative 7 over 2. And 1 minus 4 would be negative 3. We can do the same with our y's, but this time we're going to multiply by 2, then subtract 3. Negative 1 times 2 is negative 2, minus 3 is minus 5. Negative 2 times 2 is negative 4, minus 3 is negative 7. Undefined, we'll talk about that in a second. 2 times 2 is 4, minus 3 is 1. And 1 times 2 minus 3 is negative 1. So what to do with that undefined? What does that undefined represent? Well, it says when x equals 0, that's right here. What does y equal? Well, y is undefined, and that's because there's an asymptote right here, a vertical asymptote. So what happens, or where are we going to be undefined? Well, we've shifted 4 to the left, which means that our asymptote is going to be undefined 4 to the left. So the y value there should still be undefined. And I'm going to try to clarify that for you right now. As we can use mapping notation to transform our points, it's a little trickier with the asymptotes, but just by using the shift left, right, up, down, we can transform the asymptotes. So really quickly, we have a vertical asymptote, a VA, at x equals 0 from the beginning, and we're going to shift that vertical asymptote left or right based on our transformations. Well, our left or right transformation is d, and d is negative 4, which means we're going to shift 4 to the left. Therefore, our vertical asymptote is now at x equals negative 4. The d transforms and moves our vertical asymptote. Same with the horizontal asymptote, but instead of looking at d, we're looking at c. Our horizontal asymptote is y equals 0. C is down 3. So our horizontal asymptote is now going to be down 3, or y equals negative 3. So now to produce our graph, we can start by graphing our asymptotes, and then take our points and graph them around the asymptotes. The first one is our vertical asymptote at negative 4. So we can go vertically, a dashed line to represent that vertical asymptote, a dashed line. And vertical asymptote is x equals negative 4. And our horizontal asymptote is at negative 3, so that would be right here. And we have a new vertical asymptote, or horizontal asymptote at y equals negative 3. And now we can graph our points. Minus 5 and minus 5. So minus 5 would be here. Minus 5 is right here. Minus 4 is undefined. Minus 3 is negative 1. So negative 3 for x. Negative 1. So we have 2 points. Negative 3.5 is positive 1. So that would be right here. And negative 4.5 is negative 7. So that would be down here. What we have is parts of our branches, so we can connect the parts and extend towards the asymptote. And we can do the same here and extend towards the asymptote. And on this side, we can extend towards the asymptote. And here we can extend towards the asymptote. So we still have the same shape of our graph, but we've shifted it and we've vertically stretched our rational function. So that is how to transform a rational function using mapping notation.